Alrighty, this will be a relatively quick video on replacing the main oscillator on a Raspberry Pi. This is specifically a Pi 3B version 1.2. I'm pretty sure that all of the Pis in the B style format, so excluding the very first generation, up through the 3B plus. The 4 uses a different oscillator setup. I haven't really looked into it that closely. But certainly on this model and the Pi 2, the main oscillator is right here underneath the CPU. You can see all the bypass caps and such underneath the CPU, and the reason we want to replace this oscillator is just for a more stable system overall, right? Replacing the main system oscillator will give us a lot of stability if we replace it with, with a better oscillator, right? So the part that's on here is actually not a full oscillator, it's just a resonator, so it's a basic crystal. It's 4 pads. Let me get a smaller pointer here. So this is active, and this is active. This is ground. This is ground. You can see it's got a couple of decoupling capacitors. And I've replaced these basic crystals a few times with temperature compensated or external reference clock sources, and what you usually can do is just feed the clock into just one of the active pads and it'll work perfectly fine. In fact, I've already done this on a Raspberry Pi, and feeding a signal straight into this pad has worked perfectly fine. This particular part that's on here is an AEL. It's a 19.2 megahertz crystal, and got the data sheet up for it here. This is a plus or minus 20 ppm part, which in and of itself isn't really all that bad, but it's not temperature compensated, right? So one of the biggest causes of instability in any oscillating circuit is changes in temperature, especially where you've got a crystal, right? If it gets warmer, it will grow and it'll slow down. If it gets colder, it'll contract and speed up. I might have that backwards, but basically it changes with temperature, and so that makes it less stable. So one thing that exists are things called temperature compensated oscillators, and they're sort of the next step up. And basically the way these work is they have some logic in them such that they can detect changes in temperature and adjust their performance accordingly, right? So they can warm up or they can speed up or slow down based on changes in temperature, which makes for really good stability. The next step up from that is voltage controlled temperature compensated, where you can feed in an adjustable voltage to to swing that up or down as needed, sort of manually, if you don't want to use its internal routines. And then the next step up from that are ovenized oscillators, which are oscillators that are put into a little metal can that has a heater that holds them at a very stable temperature. So that makes them even more stable. And then, of course, there are controlled ovenized oscillators, right? And then you've got double ovens and all that sort of fun stuff. Thankfully, though, plain temperature compensated oscillators are really inexpensive. I don't know what the bill of materials cost for the AEL chip that's on here is, but I ordered a few temperature compensated parts off of DigiKey. Here's the underside of one, and these are I want to say these were $2.30. I've got some others that were like maybe $3 or $4, but they're really inexpensive, and they can give you really significant performance improvements as far as system stability. Right? And so what I'm going to do, so first off, it's not a drop-in replacement. All right, that's the first thing that needs to be made clear. This is not a drop-in replacement because the part that's here is just a resonator. It's just a crystal. It does not provide power. So what we're going to do, when I'm going to remove this one, and I'll show how I remove it, and then I'm going to use a little bit of glue to tack this one down, upside down, probably like right about here. And then I'll run a couple of very short wires from the output pad, which, let's see, that's pin number 4. So that's this pin right here. So, I might orient it like this, right, to get that as close as possible. Because, where we feed in power is less important. But we want the output run to be as short as possible. Anyway, something like that from there to there, real short wire. And then we'll pull in power. So this in particular, this part is a 3.3 volt part. And we can pull 3.3 volts off of this test pad marked PP8, I believe. Let me double check my notes. Yeah, that's right. PP8 is 3.3 volts. PP9 right next to it is 1.8 volts, so some oscillators are 1.8 volts. And then there are a few different places to tap off ground. So this PP3 here, for example, you can tap off ground. And I may use that. That's not quite as important. Oh, PP4 is ground as well. That's a little bit closer, so I might do that. But the first step is to go ahead and remove the old oscillator. And some folks might say that you have to use hot air for this. And I have used hot air to remove these in the past. That works perfectly fine. But there's also a sneaky way to do it with a soldering iron directly, and it works because this is a part that's all metal and ceramic, and I'm just removing it. I'm not harvesting it for any other use. This part isn't worth anything to me. So, and I apologize if this is a little bit squirrely. I have a very shallow depth of field with my macro soldering setup here, and also I'm soldering under a camera, which I don't have a ton of experience doing. So let's fire up the iron. I've got a fan going off to the side, and basically what I'm going to do is so I've got a chisel tip iron here. This is 1/10 of an inch wide, and I'm just going to lay it directly on top of the oscillator, and then flow some solder onto it, and warm it up enough such that I can basically just lift it off the board. Let me grab my tweezers with my other hand here. That'll make things a little bit easier. And there we go. Nice, clean removal. And the pads came out looking just fine. We didn't have any casualties. And then here's the part. You can see it's got a nice big blob of solder on it. Whoop! Well, that's on the floor now. Let's see. So now what I'm going to do is just wet it with a little bit of flux. And clean off the iron. And just flip the pads a little bit. Just clean them up a little. Alright, so now the next step is to figure out exactly where we want to put this guy. One thing about this part that's a little bit tricky is identifying pin number 1. So some data sheets are clearer about this than others. I believe that pin number 1 is the pin that's directly at the bottom left underneath. Was that actually a marker? Hold on, let me get my loop and get a little bit closer. You can probably see it on camera, I just can't see it through native eye. Oh, sure enough. Okay. So, oriented like this, pin number 1 is the bottom left pin. So pin number 4, which is the pin that's directly above it, so what I'm going to do is rotate it 180 degrees vertically, to sort of roll it up. So now, wait, what? So here's the part. That's pin number 1. So this should be pin number 1. Oh, I see. In the datasheet they have it rotated again. Oh, jeepers. And that's pin number 1. That's pin number 4. What I'm trying to see is what's the... I'm gonna cheat a little bit here and put a dot on pin number 1. Since pin number 1's just a ground, I'm not too worried about it. I can, 1, it has another ground, and 2, I can come back later. But I think what I might do is position this guy right here. Because that gets my clock right there. So that's a very nice short jump. Just need a very little piece of wire to go doop doop. And then this pin here directly back behind from number 4 and number oh my gosh, I misread this. That pin, number 3 is output, pin number 4 is power. Oh my goodness, how did I get this wrong? I'm not paying attention. Alright, well I'm gonna rotate it 90 degrees. So the pin caddy corner from number 1, that's right there, that is my output. I should have been a little bit more prepared before I started, but whatever. So there's that, okay, and then that guy is ground, that's ground, that's power in. I'm going to pull from this TP8 right here, since this is a 3.3 volt part, but it spits out a 0.8 volt sine wave, which is what the Pi wants. So, alright, let's move this right now. A little blob of glue. I use this E6000 stuff. I think it's a craft glue. It takes a while to dry, but that's not really a problem, because what I like about it is that, for starters, it dries a little bit tacky, whereas super glue can dry super brittle, and it also doesn't, I don't know, I've just had weird experiences with super glue. Alright, so plus it allows me to wiggle it around a little bit while I'm in stuff positioned. So I'm going to put it right, so that's pin 1. So we have 1, which in the voltage controlled version would be our voltage control. This isn't the voltage control version, so that's ground. So 1, and then that's 2 is ground, 3 right there is output, and 4 is our voltage. And so I'm going to give this a couple of hours for the glue to dry, and then I will solder on a couple of wires, and then we'll test it out. Alright, it's been a little bit now, and the part is nice and solidly in place. So we're going to start with some soldering here. I'm a big fan of this 30 gauge solid core wire wrap wire. I got a 100-foot spool of it, gosh, a couple years ago, and I still use it pretty regularly. I'm very happy with it. So I'm going to first run one between that pin that I'm sort of indicating on the oscillator to PP8 here, which is our 3V3. So, and I apologize for the squeaky chair. I know it's kind of unbearable, but what are you going to do? Get the fan yode here. Pull the iron out. Just a touch. And just a touch. And this wire is a little bit too long. Looks like it's about a centimeter too long. However, it is just power. But I think I'm going to try and trim it. Angle cutters. This isn't my good pair, but it's right at hand, so that'll work. Yeah, that'll be just fine. Maybe a little tiny bit too short. I'm just going to take it out of frame here to strip off the end of it. I've got a pair of Klein wire strippers that say they're good for 32 to 20, but honestly, their effort for really less than 26 or so is kind of phoned in. Alright. That said, I think this will work just fine right there. So, this is where I wish I had a smaller chisel tip for my iron, but between my Heiko and my Pine-Sol, I don't have anything smaller than 1/10 of an inch for chisel tips, so. What is this? I think that did it. There's a little bit of flux on it. I'm gonna get my loop-de-loop. A little closer. That looks perfectly fine. Alright. So, there's our power. And then, if I wanted to, I might do this. They say on the non-VC TCXO model that pin 1 can either be ground or not connected. And my inclination right now is to make it ground. And since both it and pin number 2 are ground, and those go up along the long edge, opposite where I just soldered the power wire, I think what I can do is I've stripped off a couple of millimeters of this wire, and I could lay it like that and tack it on, and then run it down to PP4. Oh, you know what? I could actually be really snazzy. I could strip off a couple more millimeters, because I do want a proper clock reference to ground. I could have it go from the clock pad to, you know what? I'm just gonna go from the clock pad to the crystal. I'm gonna leave that hanging for right now. Just that ground is more important. So let's see what I can do. I think this is going to be kind of tricky. This is the sort of thing that would be tricky if there wasn't a camera in the way. Now that there is, it's extra tricky. And I've got to get my curved tweezers out of my drawer, and the light is blocking the drawer. Unplug the light, put the light back. Okay. So, like here to there, that's basically what I'm thinking. And I'll arch it a little bit so it doesn't interfere with that capacitor. I'm pretty sure I could just leave this wire right there and touch it with the iron, and then come back and lift it up. Let's see if that took. I set the wire in a little bit of glue residue. Again, I've got to take it out of frame. I apologize. Sometimes you just need eyes. C. Gonna put a little bit of a right angle hook in it. And relatively speaking, this oscillator is pretty easy. This part is 3.2 millimeters by 2.5 millimeters. The other ones I ordered, I've got one here on a little homemade breakout board. Here I've also got it mounted upside down, and I have a little bypass cap for power coming in, but it is a good bit smaller. But if this works fine, I'll probably just get more of these because they're a little bit bigger. But I'm pretty sure, quick continuity test for ground here. And now actually what I'm going to do is I'm going to stop and power this thing up. And it obviously there's no oscillator connected to the CPU, so the CPU won't boot. But I do want to verify that the pin that's right there is the right pin. Right, so I've got a little improvised high precision probe, and I can poke that right down on there, and then we can look at the scope and see what the scope tells us. I'm gonna take off my macro lens adapter and point the camera at the scope and see what we see. Okay, there we go. I know this angle sucks and there's glare, but you can at least see the scope. Let's put power on the Pi. Got a red power LED. And then this will be pretty noisy because this has a few inches unisolated, but I see a wave. Let's see if I can hold it with my finger, auto set it. Ah! That looks pretty good to me. 19.2 megahertz. Looks like about 670-ish millivolts peak to peak. Sweet! Alright. So, I was pretty confident that I had the pin out right, but I didn't want to have to go and futz around with it. Alright, so back to the Pi, which I guess means I need my macro adapter. Alright, macro adapter is back on. My camera to stop dancing around on me. So what I've got, I'm going to use this piece of 30 gauge hookup wire. And basically I'm just going to use the wire itself to hold close to the pad on the circuit board on the Pi side. And then once that is attached, I can clip it and attach it to the oscillator side. First thing I'm going to do here though is put a little touch of solder on the pad. Just get my iron warmed up. A little blob of solder there. Yeah. That's not my wire. I know my finger's in the way. Just sort of holding it down here. Alright. Pretty happy with that. And then I was planning on soldering the wire onto the oscillator right there in one shot, but you know, it worked. That should focus. And I can actually just give the wire a little bit of a wiggle because this is such small wire. And, you got it. So we've got PP8, which of course is kind of hidden, but that's PP8 providing our 3 volts to that pin. Then we've got our ground feeding into the ground. We got our 19.2 megahertz right there, so pretty unobtrusive as far as little mods go. And probably what I'll do once I confirm that this works well is just kind of cover the entire thing in hot glue, just to keep everything nice and pinned down. Yeah, with that, I'll pop in a chip with the system, and we'll see if it actually boots up, if it turns on. Alrighty, so here is the Pi in question, pretty much all hooked up. I've got one of my ATGM based time hats on it. I've got a USB dongle for my keyboard here. HDMI, I haven't connected to power yet. See, it is the same module. We've still got the oscillator bodge there. So the first thing that we're going to be looking for when I apply power, there's the 2 LEDs here. So the rightmost one will be just red for power, and then the innermost one will flicker, should, as long as this mod works, flicker a little bit, and then once it has initialized the boot configuration parameters stuff, it'll switch over to blinking in a heartbeat pattern, which is what I've been using on Pis just to verify their life for a while. So here's power. It's got power. Green LED comes on. That's always a good sign. We got flickers. Monitor just woke up. And we've got a heartbeat LED, which my finger is covering. So, if I swoop up here to my monitor, oh, it's got a Thunderbolt. It does not like my power source, which is just a computer USB port. You know what? I can raise this up a little bit. Yeah, under voltage. I know. It's a crime. The GPS doesn't have a lock yet, but that's not surprising. It's reporting having a LAN IP. That's because this is a static IP I set up for somebody else. It doesn't. It's just a static. That's also why it's hanging here right now. Come on. Yeah, I know Diet Pie wants to do its checks. What am I checking? I guess I could check CGPS first. Okay, it does have a fix. Awesome. And then I can check Chronic's sources. And it doesn't have a lock yet. That's not surprising. And the date. If I had a network connection on there, it would have pulled an NTP time from one of my local servers, but I didn't plug in Ethernet. But if I go to Kearney tracking, it doesn't have any tracking data yet. Okay, we're going to let this sit for a little bit, and then we're going to come back to it once it's got a locked up time and Kearney has been able to do some analysis of the system clock. Alright, it's been a couple of minutes, and if I run Kearney C sources, we'll see that we are now locked up to the GPS. I don't have any other sources configured. You know, plus or minus 362 nanoseconds with a little bit of jitter. And if I run Kearney C tracking, this will show me the instantaneous statistics. And specifically what we're interested in right here is our frequency adjustment, right? So that would be if Kearney wasn't making any adjustments, how fast or slow would it be running? And it's running at 0.17 ppm slow, which, given the fact that this system has been booted for all of 2 minutes, is actually really good. That's really impressive. So normally, in my experience with Pis, booting them up, having them get a GPS lock, and then running Kearney C tracking, that's often much, much higher. You know, right here it's 0.17. If I have another Pi that I'm SSH'd into on my other system here, if I run, well here, let's just see my desktop system. That has it running 8.04 ppm slow. That's quite a bit different. And if I SSH into another Pi with a GPS on it, one that has been up for over a week, 5.6 ppm fast. So Kearney is still able to adjust for that, but the more stable the system clock is, period, the better things are overall. As far as taking other measurements, I'm going to sort of leave that as an exercise up to the reader. I've got a few different methods that I've been tinkering around with. The values that Kearney shows in instantaneous tracking, it of course can log as well, and so you can either log that directly to disk, or you can log that into something like InfluxDB or into an ELK stack or whatever. So there's a lot of things you can do with this data. This was all inspired by a post I read, gosh, quite a while back, over a year ago, on the Raspberry Pi Stack Overflow page about replacing the Oscillator on a Raspberry Pi. And somebody said they did it, and I'm following in their footsteps, and now I've done it too. But there's not a lot of information out there about it, so I thought I would make a video and chuck it out there. So hopefully somebody finds this interesting, and hopefully somebody can take what I've done and build upon it even further. What I have done is I've collected a bunch of information on using Kearney to have 2 identical Raspberry Pi B3 version 1.2s sitting next to each other in a thermally sealed environment for about a week, just free running, logging these values. And so now I'm going to do this again, now that one of them has this new temperature compensated oscillator. So we'll see how they compare. But anyway, yeah, this is a pretty exciting project. I mean, it's something that I was able to throw together in, a couple of hours. I could do it less if I was a little bit better prepared. But yeah, it's a pretty cool project, and easy way to provide a very significant boost of stability to what would otherwise be, a not particularly stable little hobby computer. So, thanks for watching.